Good morning, dear students. Today we will discuss about derivation of hydrothermal scheduling for short-term coordination using Kirch method. So before going to discuss about it, first we need to discuss about short-term scheduling problem. So the economic system operation of thermal units depends only on the conditions that exist from instant to instant. However, the economic scheduling of combined hydrothermal system depends on the conditions existing over the entire operating period. So this type of hydrothermal scheduling is required for 1 day or 1 week, so which involves the hour by hour scheduling of all available generations on a system to get the minimum production cost for the given time. Such type of scheduling problems, the load hydraulic inflows and the unit availabilities are assumed to be known. Here, the problem is how to supply load as per the load cycle during the period of operation so that generation by thermal power plants will be minimum. So in short-term scheduling problem, the scheduling time is considered to be 1 day or 1 week. As scheduling period is very small, the head of the water in the reservoir can be assumed constant. Short-term scheduling problem is divided into two categories. The first one is constant head hydrothermal scheduling. So here, the head of water in large capacity reservoir is assumed to be constant over a period of operation. Next, variable head hydrothermal scheduling. So here, if the capacity of the reservoir is small than the head of water, then that reservoir is variable. The load demand should meet the total generation with losses. The coordination equation of short-term scheduling problem is simple and easy. So here, some of the factors which are affecting the hydrothermal scheduling. So they are, the first one is load cycle, incremental fuel cost of thermal power stations, expected water inflow in hydropower stations, water head, that is a function of water storage in hydropower stations, hydropower generation, and last and final, the incremental transmission loss. So here, to derive the solution of optimal dispatch of the hydrothermal system, so the best method is Kirch method. So here, so we need to discuss about what are the terms are used in this method. So in this method, coordination equations are derived in terms of penalty factor of both methods for obtaining the optimal scheduling of the hydrothermal system, and hence it is also known as penalty factor method of solution of short-term hydrothermal scheduling problem. So here the terms are PGTA, power generation of high thermal plant in megawatts, PGHJ, power generation of jth hydel plant in megawatts, dou Ci by dou PGTA, incremental fuel cost of high thermal plant in rupees per megawatt hour. Omega J is quantity of water used for power generation at jth hydro plant in meter cube per second. Dou omega G by dou PGHJ is incremental water rate of jth hydro plant in meter cube per second per megawatt. Dou PL by dou PCTI is incremental transmission loss of ith thermal plant. dou PL by dou PG HJ, incremental transmission loss of jth Heidel plant. Lambda is Lagrangian multiplier. Gamma J is constant that used to convert the incremental water rate of Heidel plant J into incremental cost, where N is number of plants in total system, N minus alpha is number of idle plants, alpha is number of thermal plants, where T is time interval during which the plant operation is considered. So next we need to define the problem. So that is the optimal dispatch problem. Here it consists of objective function and constraint equation. So here we need to consider the cost, the operating cost of both the plants. So here we need to minimize the overall cost of the system, that is the objective function. So the equation is summation I equal to 1 to alpha integral 0 to t Ci dt is subjected to equality constraint equation, that is summation I equal to 1 to alpha pgti plus summation j equal to alpha plus 1 to n pghj equal to p suffix d plus pl, where pd is nothing but total demand of the hydrothermal system, pl is total transmission loss of the hydrothermal system. So here the total transmission loss is depends on the both the plants. So if this among these two plants, if any plant is nearer to the load center, the transmission loss of that plant is zero. And another constant equation is summation integral 0 to t omega j dt equal to kj for j equal to alpha plus 1 comma alpha plus 2 dash 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 n. This is like equation number 3. So where kj is amount of water in meter cube utilized during the period t in jth Heidel plant. Omega g equal to turbine discharge in the jth plant in meter cube per second. So this is the hydrothermal scheduling problem. So here we need to solve that problem by using Lagrangian multiplier technique. For that, so we need to write the equation for L. L equal to Ct plus lambda into Pd plus Pl minus summation I equal to 1 to alpha Pgti minus summation j equal to alpha plus 1 to n Pghj. So where Ct is nothing but summation I equal to 1 to alpha Cti plus summation j equal to alpha plus 1 gamma j omega j plus lambda into Pd plus Pl minus summation I equal to 1 to alpha Pgta minus summation j equal to alpha plus 1 to n Pghj. So here we need to use two conditions. So first one is dou L by dou PGTA equal to 0. Second condition, dou L by dou PG HJ equal to 0. So by using these two conditions, so you can get the value of lambda for both thermal and hydro power plant. So first, for thermal power plant, so we need to do the above equation. We need to do the above equation uh, different. Differentiate the above equation with respect to PGTA and equate it to 0. Then we will get the lambda value that equal to dou Ci by dou PGTA into 1 minus 1 by 1 minus dou PL by dou PGTA. So where 1 by 1 minus dou PL by dou PGTA is nothing but penalty factor, and dou PL by dou PGTA is incremental transmission loss. For hydro plant, so we need to do the above equation with respect to PGHJ and equate it to 0. So here we will get the lambda value equal to gamma j dou omega j by dou pgh j into 1 by 1 minus dou pl by dou pgh j. So here these are the final equations of both hydro and thermal power plant. So here, if any of the plant located nearer to the load center, so then this is a penalty factor. So this becomes 1 if the thermal plant is located nearer to the load center, and also this incremental transmission loss value equal to 0. Thank you. Thank you for watching.